So an infinite sequence is just a bunch of numbers in some kind of order that continue forever. And each of those numbers are called terms, and they're usually represented with an A and then a subscript. So the first term is A1, the second term is A2, and so on. An example of a sequence would be if we had all the even numbers, say 2, 4, 6, 8, etc. So one way to describe a sequence is it's a function where the domain is only integers. For example, if we had that sequence of even numbers, we could represent it as a function of n, where f of n equals 2n. But we can only plug in integer values for n. So if we start at n equals 1, then the first term would be 2, and then when n equals 2 it would be 4. If we plug n equals 3 in, it would be 6, and so on. But we can't plug in n equals 1.5 or anything like that. Only integer values. So another way to describe a sequence is with this bracket notation. So inside the bracket, we have the general term, which is a formula for finding the term, the nth term. And then here we have n equals 1. This is called, the n is the index, and it can be any letter. And so it says the first term of the sequence, we will plug in n equals 1. And the index does not have to start at 1. We can have a sequence which starts where the first term, you plug n equals 0 in. But it's usually either 0 or 1. And then this number here is to what number do we plug the n's into. So if it was 10, then after we plugged in n equals 10, then we'd stop. But with infinite sequences, obviously, it's always going to be infinity. So if we have this sequence where the general term inside the bracket is n over n plus 1, and the index starts at 1, that means to get the first term, we'll plug n equals 1 into this general term, which gets us 1/2. And then next we'll go up by one integer. So we plug in n equals 2 to get 2/3, and then so on and so on. So if we keep plugging in values of n, and the terms kind of get closer and closer to one number, we say that the sequence approaches a limit. So the limit of a sequence describes how it behaves as the n that we plug in approaches infinity. So if the terms in a sequence keep approaching some number L as we plug in more and more values of n, then we say that the sequence converges to the limit L. And if a sequence does not converge, then it diverges. So let's look at some examples. So if we have this sequence, you can see that since we have this -1 to the n plus 1 power, each time we plug in a different value of n, it will keep oscillating between negative and positive 1. So the terms in this sequence will keep switching back and forth between negative and positive. So even though this part right here, n over 2n plus 1, this converges to 1/2, since if we take the limit of this expression as n approaches infinity, we'll get 1 over 2. So this part of the sequence converges, but this part oscillates between negative and positive 1. So that means as n approaches infinity, then the sequence, the terms of the sequence will oscillate between positive and negative 1/2. So that even though this part converges to 1/2, the overall sequence will diverge. So in this one we have n over e to the n. So if you just think about it, e to the n will grow much faster than n as we keep plugging in higher values of n. So right away we can tell that the limit will be 0. But you can prove it with using L'Hopital's rule. So if you just take the derivative of the top and bottom, you get 1 over e to the n. And then taking the limit of that as n approaches infinity, you get 0. So this sequence converges to the limit 0. Here we have n to the 1 over n. And if we just take the limit as n approaches infinity, we get an indeterminate form. So we need to use L'Hopital's, and to do this we have to treat it as a function first. So we can write that y equals n to the 1 over n. And then to use L'Hopital's with this one, we need to take the natural log of both sides. So we get ln of y, and then taking the natural log of this, we can move this 1 over n down to a coefficient from the log properties. So the right side becomes ln of n divided by n. And now this is in the form infinity over infinity, so we can use L'Hopital's rule. So differentiating the top and bottom of this expression, we get 1 over n divided by 1. And the limit of that as n approaches infinity is 0. So the limit of the ln of y as n approaches infinity is 0. So the limit of y is going to be e to the 0, or 1. So the sequence converges to the limit 1. And a sequence only converges to a limit if the even number terms and the odd number terms both converge to the same limit. So over here we can see that the odd number terms, the first term, the third term, and the fifth term, they seem to converge to 1, while the even number terms, 2, 4, and 6, seem to converge to 0 because they keep getting smaller. So even though the even and odd number terms both converge to a limit, they are not the same limit, and therefore the overall sequence does not converge to a limit. So it diverges. And then last we have the squeeze theorem. So the squeeze theorem for regular limits also applies to the limits of sequences. So just like the regular squeeze theorem, if we have 3 sequences and one of them is always in between the other 2, and then the lower and upper sequences both converge to the same limit, then the middle sequence also converges to that limit. So if we have this sequence, and if we directly evaluate it by plugging in n, the limit as n approaches infinity, we'll get infinity over infinity. But we can't use L'Hopital's since we can't differentiate n factorial. Because if we treat it as a function, y equals x factorial, then this is not a continuous function, since the factorial is only defined for integers. You can't have 3.5 factorial. So since this function is not continuous, it's not differentiable. So we can't use L'Hopital's. So what we do is expand the general term. So n factorial is 1 times 2 times 3 up to n, and n to the n power is just n times n times. And so if we factor out a 1 over n, then we're left with this. And so notice how this part of the expression will always be less than or equal to 1. Because on the bottom we have a bunch of n's, while on the top we have 1 n and a bunch of numbers less than n. So, and if n is 2, then it will just be 2 over 2, or 1. So this is always going to be less than or equal to 1, which means that since this general term is equal to 1 over n times this term, the general term is always less than 1 over n. So now we have upper and lower bounds for the general term. The general term is always going to be greater or equal to 0, and it's always going to be less than or equal to 1 over n. So these two terms of the sequences sandwich this term. And since 0 and 1 over n both approach 0 as n approaches infinity, they both converge to the same limit. The middle function, or middle sequence, must also converge to that same limit. So the general term approaches 0 as well, and therefore the sequence that we started with converges to 0 by the squeeze theorem.